Nadiwal, and here's my circuits and capacitors lab for Physics 2212. The main purpose of this lab was to predict the behavior of circuits containing resistors and series and parallel, as well as use multimeters to measure conventional current and potential differences. Lastly, we'll be examining the behavior of ohmic resistors and capacitors. The main physics principles was Ohm's law, which states that voltage equals current times resistance; capacitance, which is equal to charge over voltage; the loop rule, which states that the sum of all potential differences around a circuit loop equals zero; as well as the node rule, which states that the sum of the currents flowing into a junction equals the sum of the currents flowing out. So for our setup, in order to create an initial series circuit, I used the circuit construction kit program from the Colorado PHYS project. I constructed the circuit with two 1.5 volt batteries, one 45 ohm resistor, 100 ohm resistor, and two ammeters placed in the configuration shown in the image to the right. By using Ohm's law and the loop rule, we can predict the current to be 0.0204 amps, since current is equal to voltage over resistance. We can confirm this prediction by reading the ammeters in the circuit program, which reads 0.02 amps as shown in the right. If the ammeters are reversed, they still read the same value. If we replace the first ammeter with a voltmeter, we can see that the voltmeter measures a voltage of 3 volts while the ammeter reads a current of 0 amps. This is because the current is no longer closed, thus the voltmeter can measure the potential difference to be 3 volts from the battery. This is because the voltmeter does not allow current to flow through it, since it has an infinite internal resistance, which is also why the ammeter reads 0 amps of current. In order to measure the round-trip potential difference of the circuit, we can sum up the individual potential components of separate segments of the loop. The loop tells us that the total round-trip potential difference in a closed loop should be equal to 0, and if we sum up the segments through the value shown in the chart, we can see that it is true. If we were to create a graph of the potential versus the position around the loop, we would get what is shown. The differences in potential from the previous slide are graphed and still result in a potential difference of 0. If we were to use our calculator current to find the resistance of the resistors, we would use the formula resistance equals change in potential over current. This calculation results in a resistance of 48.02, 100, 0 and 0 ohms for the 47 ohm resistor, 100 ohm resistor, wire, and ammeter respectively. While the voltmeter is used to measure potential difference, it does not alter the ammeter reading since it has an infinite internal resistance. If we were to place the second ammeter in parallel with the 100 ohm resistor as shown in the picture, the ammeter readings would increase to 0.06 amps. Due to the node rule, the current is split with a parallel path, resulting in less resistance based on the equation current equals voltage over resistance. If the resistance decreases, the current will increase. RC circuits. Next, we'll be creating an RC circuit, which will consist of a 9 volt battery, a 10 and 20 ohm resistance light bulb, and a 200 mF millifarad capacitor placed in the configuration shown in the image. As the capacitor is charging, the light bulb starts off bright and begins to fade. When the battery is disconnected and the capacitor is discharging, the same observation while the battery is disconnected and the capacitor is discharging, the same observation was made. During both events, the current slows down as time moves on, and when the capacitor discharges once the battery is removed, the current reverses directions. We then measured the time it took for the capacitor to charge and discharge using both the 10 and 20 ohm resistance light bulbs. The 10 ohm bulb took 6.45 seconds to charge and 9.39 seconds to discharge, while the 20 ohm bulb took 14.07 seconds to charge and 18.72 seconds to discharge, which is explained by the current traveling slower in the 20 ohm circuit due to more resistance. In order to determine the time dependence of the capacitor in the loop with 30 ohm light bulb, we will keep track of the voltage of the capacitor for each second in a 20-second interval. The voltage difference decreases exponentially with time as shown by the upper equation. If we then take the natural log of each side and graph the natural log of delta V over V naught, we will get the graph shown in the PowerPoint. The slope of the graph will give us negative 0.166, which we can set to negative 1 over RC. From this, we can calculate the time dependence constant to be around 6.02 seconds. The time dependence of 6.02 seconds was similar to an expected value of 6 seconds, with the percent error of only 0.33%. The reflectiveness graph was conducted in real life with, or 0.033%. The reflectiveness lab was conducted in real life with an actual ammeter instead of a simulated ammeters. The real life readings would be less than the true values. This is because real life ammeters have resistance, which would affect the current readings due to current equals voltage over resistance formula. Similarly, if the lab were to be conducted in real life with a real battery and capacitor, the ideal model would predict the capacitor to charge instantly. However, the charge time for the capacitor would be slightly longer in real life than that in a simulated lab because real models would have resistance within the circuit, which would slow down the current and thus take the capacitors more time in order to charge. Thank you.